Hello everyone. What we'd like to do in this video is take a look at the graph of a logarithm. So in last video we learned that what is a logarithm? It's just the inverse of an exponential function. A lot of students get thrown off, I think, with just the notation of a logarithm, maybe because there's 3 letters in it, log, but it's just notation. What is a logarithm? It's just the inverse of an exponential. Let's take a look at what they look like graphically, though. We want to know, what does the graph of a logarithm look like? So let's brute force it with what the definition of a logarithmic function is. It's the inverse of an exponential. Let's first graph an exponential function. Okay, so to explore, this is us doing math research. We're exploring. So here we have the function f of x, which is equal to 2 to the x. Okay, we know how to evaluate. An exponential function. Let's plug in a few values. Let's say we plug in 3, for example. So what would be the output? What would be f of 3? We'd get 2 cubed. I hope you believe that 2 cubed is 8. If we plug in 2, I hope you believe that 2 squared is 4. If we plug in a 1, I hope you believe that 2 to the first power is 2. 2 to the 0th power. Well, what would 2 to the 0th power be? Well, anything to the 0th power is just 1. Okay, I kind of want to just maybe pause here for a second, just kind of noticing this pattern here about raising 2 to a power. When I raise 2 cubed, I get out 8. When I do 2 squared, I get out 4. When I do 2 to the first power, I get out 2. Notice what's happening here? That each step here, I'm just dividing by 2. So if you have trouble understanding why should 2 to the power of 0 be 1, or what would it mean when I raise 2 to 0 or 2 to a negative number, just follow the pattern. 8 divided by 2 to get 4, divided by 2 to get 2. Take 2 divided by 2 to get 1. That's why 2 to the 0 power should be 1. So if we repeat the process, what should 2 to the negative 1 be? We'll just continue the pattern. Divide by 2, divide by 2, divide by 2. So 2 to the negative 1 power should be 1 divided by 2, or 1/2. Similarly, 2 to the negative 2, I hope you believe, is 1 over 2 squared, or this should be 1/4. Or 2 to the negative 2 is divide by 2 twice, that's 1/4. Okay. And similarly, we get that 2 to the negative 3 should be 1/8. So let's graph this. Okay. One, 2, 3, -1, -2, -3. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's plot 2 to the x. I know we've already done this, but it's going to be important when we do the inverse. So let's see here. We plugged in 3, we got an output of 8. We plug in 2, we got an output of 4. We plug in 1, we get an output of 1. I'm sorry. Should line these up. You plug in 1, you get an output of 2. You plug in 0, you get an output of 1. You plug in -1, you get an output of 1/2. You plug in -2, you get an output of 1/4. You plug in -3, you get an output of 1/8. So we have our, maybe I'll graph it in green. We're going to graph this in green, the exponential function in green. So what is this? What does it look like? It looks like this. No surprise. This is 2 to the x. Okay, but now we want to graph its inverse. Okay, notice here, also remember that exponentials have horizontal asymptotes. So what do we want to do when we want to graph the inverse? Well, what we want to plot now for the inverse is, let's plug in x. But now we want to graph what would be the inverse function. The inverse of an exponential, the inverse of 2 to the x, we have denoted as log base 2 of x. So remember how inverse functions work is their inputs and outputs flip. So all of these inputs and outputs we need to flip. So I should have an 8 here and a 3 here. I should have a 4 here and a 2 here. We should have a 2 here and a 1 here. We should have a 1 here and a 0 here. We should get a 1/2 here and a -1 here. We should get a 1/4 here and a -2 here. We should get a 1/8 here and a -3 here. So since it's an inverse, I'm just flip-flopping the points. The domain and range is flipped. So now let's graph the inverse. We're going to graph it in red. We're going to graph it in red. Let's see what it looks like. Okay, I need to go further out. So this is, what, 3, 4, 5, 6, 7, 8. Okay, what's true about the logarithm? Well, if you plug in 8, you get an output of 3. Okay, if we plug in 4, we get an output of 2. If we plug in 2, we get an output of 1. If we plug in 1, we get an output of 0. If we plug in 1/2, we get an output of -1, -1, -2, -3, -4. Okay, if we plug in 1/2, we get out -1. If we plug in 1/4, now we get out -2. If we plug in 1/3, now we get out -3. Notice here it's getting closer to the y-axis. Here we have it. Here we have it. Here we have it. Here is the equation of the logarithmic function. Now notice here that it has a vertical asymptote. It must have a vertical asymptote. Notice as we're getting closer to 0, it's arbitrarily, as the inputs are getting closer to 0, the outputs are getting closer to the y-axis. This is log base 2 of x. And notice, I know my scaling's a little bit off, but notice, look at this symmetry. Look at this symmetry. Look at this symmetry. It's beautiful. It's beautiful. It would be even more symmetric if I just would have drawn a like scale. But these are inverses. They're reflections over the line y equals x. Let's make sure we can see this clear. There's a little bit of a glare. But look at that beauty. Look at 2 to the x and look at log base 2 of x. Look at those functions. They're inverses of one another. What we have here in red is the picture of log base 2 of x. Beautiful, beautiful. Notice here that logarithms have asymptotes. They have horizontal asymptotes. Okay, similarly, if we would have done something slightly different, let's go ahead and erase this really quick. Let's kind of get a general picture of this. Let's get a general picture of this. Okay, so if we have a function, let's say f of x, if we have f of x, which is equal to b to the x, remember those conditions on b. B has to be greater than 0 and b can't be 1. Okay, well, the picture, there's 2 different pictures here. Well, for a base that's bigger than 1, if the base is bigger than 1, it's exponential growth. So the picture of this would look like this. This is the graph of b to the x. Okay? If b is a fraction, remember now it's exponential decay. It's exponential decay. Okay? We have this nice point here. This is the point 0 and 1. This is also the same point 0 and 1. They have, do it in green, they have horizontal asymptotes. Okay, now if we're thinking about logarithms, those are the inverses. Need a little bit more room. Now, if we want to think about the graphs of the logarithms, log base b of x, well, they're just going to be these pictures just reflected over the line y equals x. So what are they going to look like? Okay, well, if b in the base of the logarithm is bigger than 1, this is kind of what we did with log base 2 of x. Well, since it's a reflection over the line y equals x, this horizontal asymptote, think about the line y equals x, this horizontal asymptote becomes a vertical asymptote. This horizontal asymptote, if I reflect it over the line y equals x, becomes a vertical asymptote. We now have a vertical asymptote. Also, if the point 0, 1 was on b to the x, then the point 1, 0 is on log base b, So this graph will look like this. They're reflections over the line y equals x. Here's the graph of b to the x for b greater than 1. This is the graph of log base b of x for b greater than 1. Well, what if b is a fraction? Well, same thing's going to happen. This horizontal asymptote will become a vertical asymptote. Okay? And we still have the point. We'll still have the point here. 1 and 0. 1 and 0. So what is this going to look like? Let's see. Well, since it's reflected over the line y equals x, on the y-axis it'll be approaching infinity. So this will be its graph. This will be the graph of log base b of x for when the base is a fraction. So here's what the general shape of a logarithm looks like. Let's make some nice observations here about both of these. Okay, I need a little bit more room, so I'm gonna erase just maybe I'll erase just most of this. All right, yeah, we'll erase this. Okay. Well, for f of x, for b to the x, remember what its domain and range is. So for an exponential function, the domain of an exponential function is we can plug anything we want into it. So this would be all real numbers. This is just a super fancy way. to say that x is a member of the real numbers. This is just saying that x can be between negative infinity and infinity. And what is the range? What is the range of an exponential function? What is the range? Well, if we remember the graph, it goes like this. You're only going to get outputs bigger than 0. So the outputs here is all y greater than 0. Okay? Well, if we're thinking about the inverse of this, if we're thinking about log base b of x, okay, we still have the same conditions that b has to be greater than 0 and b can't be 1. Okay, well, if we're thinking about the domain and range, go back in the video a little bit and look at those pictures, but I don't need the picture to know what its domain and range is because I know since it's an inverse function, its domain and range are just going to flip-flop. So for the logarithmic function, its domain is going to be all x such that x is greater than 0. Also, what is the range? The range is going to be all y such that y is a real number. So maybe I should have said this is the same thing as from 0 to infinity. So what is the domain and range of a logarithm? Well, you can only plug in numbers strictly bigger than 0 into a logarithm. So the domain of a logarithm is from 0 to infinity. The range of a logarithm is from negative infinity to infinity. Okay, we need to pay attention to this because we now have a new domain restrictions. The math gods are going to be giving us another list on our commandments, another list on our golden rules of math. We have a new thing to add. What can we do? Let's kind of erase this a little bit. Pay attention. I can only plug in numbers strictly bigger than 0 into a logarithm. So this gives us a new domain restriction, a new rule, a new golden rule in math. We had our domain restrictions. Okay, what was the list? What was the first thing we couldn't do? Thou shalt not divide by 0. We can't divide by 0. 2. What else did the math gods tell us that we can't do? We can't take the even root of a negative number. Can't take the even root of a negative number. In the world of real numbers, this is forbidden. Okay, we now have a new rule. Thou shalt not take the logarithm of a negative number or 0. What can't we do? We can't take the logarithm of a negative number or 0. We always have to remember this. These type of domain restrictions, this isn't one of those things where, okay, I'm going to get through this domain section in this class and I'll never have to remember it again. No, through the rest of your math career, you're always going to be asking yourself domain questions. It's super important. Okay, let's do a quick example. Let's do a quick example of finding the domain of a function. But now we'll introduce logarithms. Okay, so simple example. So we're going to find the domain of the following. Okay, so let's say we have f of x, which is equal to log base 5 of 8 minus 2x. Okay, well, what do we need to have? What do we need to be true here to find the domain of this? Well, the third rule says that we can't take the logarithm of a negative number or 0, so whatever's inside of the logarithm has to be strictly bigger than 0. So here we need 8 minus 2x to be strictly bigger than 0. Remember, we can't take the logarithm of 0. So we could solve this. We could, subtract 8 from both sides. So we'll get a negative 2x is greater than negative 8. We could divide both sides by negative 2, but be careful. Remember, when we divide or multiply both sides of an inequality by a negative, we got to flip the sign. So this would say that x has to be less than 4. That is the domain. So the domain, if we want to write it in, we'll write it in a couple different ways. So here, the domain of this function is all x, such that x is less than 4, or in interval notation, we can plug in numbers from negative infinity to 4. So here's the domain. Let's do another example. Let's say we have g of x is equal to, how about the natural log of x squared minus 5x plus 6. Let's try to find the domain of this function. Go ahead and pause the video and give it a shot on your own. Okay, let's do it. Let's think here. Well, what do we need to be true? We can't take a logarithm of 0 or any negative numbers. So what do we need? We need x squared minus 5x plus 6. Maybe I should have wrote this in green. We need x squared minus 5x plus 6 to be strictly bigger than 0. So what we want to know here is, when is this quadratic bigger than 0? This is a situation where we're going to want to factor and make a sign chart. So this factors to what? What is this going to factor to? I think I need combinations of 2 and 3, and I think they both need to be negative. Okay, so these multiply to give me a positive 6, and they add to give me a negative 5. Okay, let's make a sign chart. Okay, when is this exactly equal to 0? Well, at 2, and at 3. Now we can make a sign chart. You could also kind of think to yourself that, what is this? This is a happy face parabola, and it has roots at 2 and 3. That means it crosses the x-axis at 2 or 3. So you could kind of think to yourself, if we were graphing this parabola, it would look like this. So a sign chart is, well, the graph is positive over here, it's negative over here, and it's positive over here. So you could fill that in. Or, if you don't like those graphical arguments, just make a sign chart, test some points. A number less than 2, how about 0? Well, if we plug 0 into here, 0 minus 2 is a negative number. 0 minus 3 is a negative number. A negative and a negative makes a positive. Pow, 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 pow. Okay, pick a number between 2 and 3. How about 2.5? Okay, 2.5 minus 2, 2.5 is bigger than 2, so it's positive. And 2.5 minus 3, well, 2.5 is smaller than 3, so that'll be negative. So a positive times a negative is a negative, so it's negative in here. And similarly, pick a number bigger than 3, I don't know, 5 or 100 or 1,000,000, anything bigger than 3. Okay, well, 5 minus 2 is positive, and 5 minus 3 is positive. A positive times a positive is a positive. Okay. So with our sign chart here, now we can think about, when is this quadratic bigger than 0? Well, it's bigger than 0 when what? Well, when x is bigger than 3, or when x is smaller than 2. Notice I can't include 2 and I can't include 3 because I need to be strictly bigger than 0. So here the domain, we could write the domain will be equal to all x, such that, well, x could be less than 2, or we could have x could be greater than 3. Or you could say that this is the same thing. I guess we want to write interval notation. This is from negative infinity to 2 union with 3 to infinity. So this is the answer. Let's do one more. Let's do one more. Let's do one more. Okay, let's say, for example, we have the function h of x, and let's say that it's the square root of x minus 2 minus log base 7 of 10 minus x. Okay. Go ahead and pause the video and try to find the domain of this function. Okay, let's do it. I have 2 pieces here I'm worried about. 2 pieces we're worried about. I'm possibly worried about taking the square root of a negative number, and I'm possibly worried about taking the logarithm or log base 7 of a negative number or 0. So there's 2 things I have to consider. Okay, so the first thing is this piece right here. Well, what do we need? We need x minus 2 to be greater than or equal to 0. So the first condition we need is for x to be bigger than or equal to 2. As long as x is bigger than or equal to 2, this piece of the function is satisfied. It's happy. Okay, over here, log base 7, okay, I need to make sure that what's inside of the logarithm is strictly bigger than 0. A question that you might be asking yourself is, does it ever matter for the restrictions what the base is? No. Every single logarithm of every single allowable base will always have the condition that you cannot take the log of any base of a negative number or 0. So it doesn't matter what the base is, whatever is inside here will always have to be strictly bigger than 0. So here we need 10 minus x, in this case, to be strictly bigger than 0. For square roots, they can be bigger than or equal to 0. For logarithms, strictly bigger than 0. Okay, what could we do here? Well, we could what? Subtract 10 from both sides. So here we would have that what? Negative x would be greater than negative 10. Multiply both sides by a negative. And we get that x, remember I multiplied by a negative, I gotta flip the sign, x will have to be less than 10. So I have 2 conditions we have to look at. Okay, the first one is we need x to be bigger than 2. We need x to be bigger than or equal to 2. So here's 2. It can be bigger than or equal to 2. But at the same time, we need x to be strictly less than 10. Okay. So I need to figure out what works for both of them. I need to look at the intersection of these two sets of numbers, and that'll be this region right here. This is the region. These are the set of inputs that this function can eat. Okay? So x has to live between 2 and 10. It can be 2, it can't be 10. So what's the domain? Well, we'll write it in two different ways. In set builder notation, well, x can be between 2 and 10. It can be equal to 2, it can't be equal to 10. Or if we want to use interval notation, we can have the numbers between 2 and 10. Okay, we put a hard bracket on 2 because we can plug in 2. We put a soft bracket on 10 because we can't plug in 10. Here is the domain of this function. Okay, now what we want to do, we know a little bit about domains. This is really similar to what we've been doing before with domains. It's just a new rule. We have to watch out for logarithms. Okay, now let's talk about graphing logarithms. You're going to find that the way we graph logarithms is going to be no different than how we graph exponential functions. There are key features to logarithms, and we're just going to follow them through the transformations. Okay, so let's talk about graphing. Graphing logs. Okay, so for f of x, let's say f of x, let's say it's an exponential function. When we are graphing these, remember that there were key features that we followed through the transformations. What point is on b to the x? Well, they'll always have the point 0. You plug in 0, you'll get an output of 1. If you plug in 1, you'll get an output of b. And the other feature is they had a horizontal asymptote. It had a ha at y equals 0. At y equals 0, I mean the horizontal asymptote is the line y equals 0. Okay, well, what about logarithms? Well, remember, all a logarithm is the inverse of an exponential. That's what they are. Don't let the notation confuse you. It's just the inverse of this thing. So what's true about inverses? Things flip-flop. So if these were key points on b to the x, what will be the key points on the logarithm? The flip-flops. The flip-flops. 1, now it'll be 1 and 0. So if you plug in 1 into a logarithm, you'll get out 0. If you plug in b into a logarithm, you'll get out 1. Okay? In this case, b to the x, the exponential function, had a horizontal asymptote. We're reflecting over the line y equals x. The logarithm will have a vertical asymptote. Here we had a ha, here we have a va. We have a vertical asymptote, and it'll be the vertical line x equals 0. So when we're graphing transformations of logarithms, we're going to follow these key features through the transformation. Now, I just want to make a comment about how to think about that these are really values on a on a log-based b function. For example, how can we think about these? What's the best way to think about it? Let's say if we have log base 3. Well, I'm claiming that if you plug 1 in here, you should get an output of 0. Why? Maybe, well, think about it. What is the output here? What is the output? This would be the same thing as 3 to what power gives you 1? 3 to what power gives you 1? Well, remember that any number to the 0th power is 1. Remember that 3 to the 0 is equal to 1. So this is saying that 3 to the x would be equal to 3 to the 0. Boom! Boom! Dropped a base. X would be 0. So when you plug in 1, you get the output of 0. This would be the same for any base. If I put a b here, if I put a b here, I put a b here, I put a b here. B to what power? B to what power gives you 1? Well, I know b to the 0 is always 1. So dropped a base, boom, x equals 0. Similarly, that's why when you plug in 1 to any logarithm, you're going to get out 0. Okay, well, what about, let's do log base 7. It's saying if I plug in 7, or if I plug in b, we should get an output of 1. So here, if we plug in 7, why do we get an output of 1? Well, this is kind of saying 7 to what power gives you 7? I hope you believe that's 1. Or you could say this is equal to x. So 7 to what power gives you 7? Well, this is 7 to the first power. Boom, boom, drop the base. X equals 1. So that's why when you plug in the base, you're always going to get an output of 1. Okay, so we could just replace all these 7s with b's if you like. B. Sweet. Okay, so let's do some examples. Okay. So example. Let's say that we want to graph. Let's graph f of x, which is equal to log base 3 of, how about x minus 4 plus 1. Go ahead and pause the video and give this a shot on your own. Think about the key features on the parent function and think about what transformations are happening to it and run those numbers through the transformation and see what the graph should look like. Okay, let's do it. So when we want to graph this transform logarithmic function, the first thing we should ask ourselves is, what is the parent function? The parent function is log base 3 of x. And what are the key features? Well, we know if we plug in 1, we get an output of 0. If we plug in 3, we get an output of 1. And logarithmics have vertical asymptotes at x equals 0. Or it's the vertical line, the equation of the vertical line is x equals 0. Okay, so now we want to think about what has happened to this logarithmic function. What has happened to the parent function? Well, notice that right here that we're subtracting 4 directly from the x value. That's going to shift our graph to the right 4 units. Okay, what is this plus 1 going to do? I'm adding 1 to the outside of the function. That's going to shift my graph up 1 unit. Okay, so let's make a little table. Okay, so here's log base 3 of x. Here's the parent function. Key features 1, 0. 1 and 0. Okay, we also have 3 and 1. And we have the vertical asymptote, x equals 0. So what have we done? We're shifting it to the right 4 units. And then we're shifting it up 1 unit. Okay, let's run these points through this transformation. Okay, so I'm physically moving the graph to the right 4 units, so I want to add 4 to all the x components, or all the x coordinates. So 4 plus 1 is 5, so 5 and 0. Let's see, 4 and 3, that's 7 and 1. It'd be 7 and 1. Okay, I have this vertical asymptote, and I'm physically moving it. I'm physically moving it to the right 4 units. So here, the new vertical asymptote will be x equals 4. Okay, and now we're shifting it up 1 unit, so I want to take all my y coordinates and add 1 to them. So now we'll be at the point 5, 1, 7, 2. Now I have this vertical asymptote. It's an infinite line, and I'm taking that infinite line and I'm moving it up 1 unit. Well, it's still going to be that same infinite line, so the vertical asymptote won't be affected. It'll still be at x equals 4. You can also think about this as, hey, when I'm shifting it up, I'm affecting my y values. Well, this is like an x. This is an x, so it's not affecting the x's. Okay, so now we can graph this. Okay, I need to go my vertical asymptote. I need to is the vertical line x equals 4. Okay, if we plug in 5, we get an output of 1. So 5, we get an output of 1. And if we plug in 7, 5, 6, 7. If we plug in 7, we get an output of 2. Right here. So now these points should guide us. Now in this case, for logarithmic functions, they'll either always be on the right side of the asymptote or the left side of the asymptote. In this case, since these points are on the right side of the asymptote, the entire graph will be on the right side of the asymptote. Okay, so what we're going to have here is this graph. These points should kind of guide us. We have that the graph of this function will look like this. Here's the graph of log base 3 of x minus 4 plus 1. Let's do another example. Okay, let's say we want a graph. Let's say that we want a graph. How about g of x? Let's say this is equal to. Let's say this is equal to. How about negative log base 2 of how about x plus 3. Go ahead and pause the video and give this one a shot. Okay, let's do it. So we have log base 2 as our parent function. What are the key points on log base 2? Well, if you plug in 1, you'll get an output of 0. If you plug in 2, you'll get an output of 1, and it has the vertical asymptote, x equals 0. Okay, let's see what's happened to it. Well, what we've done here is we've added 3 to the x component, so that's going to shift our graph to the left 3 units. So we'll shift it to the left 3 units. And now what's this negative going to be doing? The negative's on the outside of the function, so it's taking all our outputs and making them negative. It's taking all our outputs and making them negative. This is a reflection over the x-axis. This is a reflection about the x-axis. Okay, so let's do it. Let's do it. So we have log base 2 of x. We have the point 1, 0. We have the point 2, 1. And we have the vertical asymptote, x equals 0. Okay, remember that we need to make sure to do reflections and stretches before we do shifts. So in this case here, we need to first reflect about the x-axis. So reflect over the x-axis. And then we also need to shift it to the left 3 units. Okay, so when we're reflecting over the x-axis, don't let the word x-axis confuse you. We're not going to throw negatives on the x values or on the x coordinates. This is a reflection over the this is a reflection over the x-axis. This affects the y values. So all my y values will be negative. Okay, well, if I throw a negative on 0, I hope you believe that negative 0 is the same thing as 0. Okay, this will be 2. 1 times negative 1 will get a negative 1. And if I multiply this by a negative, I mean, think about this vertical asymptote. I'm reflecting it over the x-axis. It's still going to be the same vertical asymptote. So it'll still be x equals 0. Now what are we going to do? We're going to take these points and we're going to physically move them left 3 units. So I'll subtract 3 from all the x components. So we'll get a negative 2 and 0. 1 minus 3 is negative 2. Okay, 2 minus 3, that's negative 1, and we'll negative 1. And now the vertical asymptote will be at x equals negative 3. I'm moving it to the left 3 units. Okay, we can graph this now. We can graph this. Let's do it. What's this going to look like? Okay, so let's see, 1, 2, 3. Here's negative 3. Here's our vertical asymptote. We have the point, this is negative 1, this is negative 2, this is negative 3. We have the point negative 2, 0, negative 2, 0, and the point negative 1, negative 1. Okay, this should now guide us to the graph. The graph always has to be on the right of this vertical asymptote. So the graph will look like this. Here is the graph of negative log base 2 of x plus 3. Let's do one more example. Okay, let's say, I guess as another example, our last example, is let's say we want to graph, how we call it h of x, so we're going to graph. Let's say this is, let's do log base, let's do log base 4 of, how about a negative x plus 3, and let's multiply 2 out front. Let's go ahead and give this one a shot. Okay, pause the video and give this one here a shot. Okay, let's do this. So our parent function is log base 4, of x. Okay, what are the key points on this? Well, if we plug in 1, we get out 0. If we plug in 4, we're going to get an output of 1, and we have the vertical asymptote x equals 0. Okay, what has happened? Okay, the first thing I'm going to notice is I'm multiplying 2 out front. We're multiplying 2 out front. This is a vertical stretch by a factor of 2. So a vertical stretch by a factor of 2. Now, this is where we need to be super careful. You would definitely be correct that we have a negative on the x value. I'm applying a negative to the x. So we're taking our x values and we're making them negative. This will be a reflection over the y-axis. But you might also be tempted to think that, we're adding 3. You might be tempted to think that we're actually shifting the graph to the left 3 units. But we would be incorrect. When we're looking at horizontal shifts, we have to know what is acting directly on x. Notice I'm adding 3 to a negative x. I want to know what number is exactly affecting the x. We actually have to factor out this negative. We've got to be a little bit careful. This is the same thing. I'm going to kind of rewrite this. This is the same thing as 2 times log base 4. I need to factor the negative off of the x. So this is a negative, and now we'll have an x minus 3. So now I can see actually we're subtracting 3 directly from x, so actually we're shifting the graph to the right 3 units. So we got to be careful. So whenever there's a coefficient or there's something on the x and we want to figure out a horizontal shift, you got to factor that piece out to see the true shift. Okay. So this is a vertical stretch by a factor of 2. This negative here, this is a reflection. This is a reflection about the, this is a reflection about them affecting the x values. This is a reflection about the y-axis. And this minus 3, this is a shift right 3 units. Okay, let's do it. Okay, so we have log base 4 of x. Okay, we have the point 1 and 0. We have the point 4 and 1. And we have the vertical asymptote x equals 0. Okay, we got to do vertical stretches first. We're going to do any sort of reflections and stretches first. So how about we first vertically stretch by 2. And then let's do a reflection about the y-axis. Now you could have done these 2 in any order as long as you're doing these 2 first. Okay, what else are we doing? We are also going right 3 units. Okay? So a vertical stretch by a factor of 2, what are we going to do? We're going to take all our y values and multiply them by 2. So 0 times 2 is still 0, so we'll still have 1 and 0. Okay, now we're going to have 4. I'm going to take the y value and multiply by 2, so 1 times 2 is 2. Okay, you could think that, this vertical stretch is affecting y values, so it shouldn't affect this x, but also think that we have this, this infinite horizontal line, and if you're stretching the infinite line by a factor of 2, it's still that same infinite line. So we'll still have the vertical asymptote x equals 0. Okay. Now we're going to reflect this over the y-axis. We're going to reflect this over the y-axis. We're reflecting this over the y-axis. We don't change the y values. This is affecting the x values. So we want to make all our x values negative. So this will now be -1, 0. This will be -4, 2. And, well, this is the y-axis. If we're reflecting about the y-axis, well, it's going to stay put. So this is still x equals 0. Okay, now we're physically going to move it to the right 3 units, so we'll add 3 to the x components. So 3 plus -1 is 2, so we'll get 2, 0. We'll get, what, -1, 2. So what, 3 plus -4 is -1. And now we're taking this vertical line, you know, the y-axis, and we're moving it to the right 3 units. So our new vertical asymptote will be x equals 3. Okay, let's graph this. I'll graph it right over here. Okay. Do a little mini sketch right here. Okay. Ooh, let's do this. Okay. 1, 2, 3. Here's our vertical asymptote. Okay. We also have the point 2 and 0. So here's 2 and here is 0. So this point is on the graph. And also -1, 2. Also -1, 2. So here's -1 and 2. -1 and 2. Okay, so now we can sketch this. This should kind of guide us. Notice we're on the left side of this vertical asymptote, so we're going to stay on the left side. This graph will look like this. So here is the graph of 2 times log base 4 of -x plus 3. I hope you enjoyed this video. What we're going to be doing in the next video is we're going to start learning about log rules. So there are a lot of exponential rules. So for example, you know that, you know, if you take x cubed times x squared, that's the same as x to the power of 3 plus 2. There's all these exponent rules. But exponentials and logarithms are deeply connected. So if there are exponential rules, there's probably logarithm rules. So we're going to learn about logarithm rules, and then we're going to start using them to solve more complicated exponential and logarithmic equations. We'll see you there. Take care.